I will be talking about the practical side of data science using some examples and a lot of interaction. Please feel free to interrupt me at any point of time and ask any question. I will try to answer them to the best of my knowledge. Okay, so I have labeled these presentations as perspective and data science uh, because most of the time we pursue data science, but we often forget the perspectives in data science. So this is my very small attempt to start a dialogue on perspective and data sciences. Okay, so we'll start. So when you look at this plot, which is the introductory plot of this presentation, how do you interpret it? What is it that strikes out to you? What do you see when you look at this plot? Anyone?
Wavelet transforms.
Okay. So if you look at the title of this plot, it says a Google Trends chart of Google researchers for the term analytics between 2006 and 18. So this plot is basically showing you a trend of the search term analytics between 2006 and 2018. So now, what do you understand on this plot? So Sneha is mentioning day-wise search stats of what analytics. Okay, so when we club all this day-wise statistics of the search word analytics, what is the story that you are seeing in the trends? What is the shape of this plot telling? Anyone wants to take a hint? So there are no right and wrong answers. Just whatever is coming on the top of your head. It's rising, it's trending. Okay. So excuse me for not writing what is on the y-axis, but it is some parameter of that shows the the frequency with which the word analytics has been searched. I'm not sure what Dr. Avinash is trying to say by SN42. Could you please confirm, sir? Okay, so from this plot, we can see that the term analytics has been widely searched term, and the trend is not going to die out any soon. So that means that data science, data analytics are something that are very much a contemporary part of our lives. And if we are involved in any kind of scientific discipline that relates to analysis of data, be it qualitative, quantitative, numerical, or textual, analysis has become a I wouldn't say a prominent, but more than prominent part of our lives, and both academic research and daily life. So, this simple Google Trends chart is enough to demonstrate the weightage of the analytics word, and that we will try to explore in coming lectures. Slides. So, okay, so there will be a lot of plots and diagrams in this presentation just to provide fodder to your minds. So again, this particular 2D plot shows about the growth of analytics and data science master's degree programs in United States. So just pause on this PPT for a moment, and anyone wants to take a dig at how to interpret this plot. What do you see when you look at this plot? Any hints? So you can see that from 2012 onwards, and in 2021, you can see that there has been a surge of cumulative number of programs in data science, business analytics, and data analytics. So that means, so look at the figure in 2012. There were hardly any number of programs related to data science, business analytics, and data analytics. But now, 9 years later, we can see a huge increase in these programs. So anyone who wants to guess what could be the reason behind this trend? Why are we seeing such an increase in the number of programs related to data science, business analytics, and data analytics? What do you think could be the reason behind this increasing trend? Okay, so Rohini mentions that you see a positive correlation between what, Rohini, if you can help us to understand. Rika is mentioning that there is huge amount of data. Okay, Sagar is mentioning that it gives profit in business, effective decision making because we are moving towards digital world. Okay, so you see, as the need for professionals which are thorough in the science of analyzing data and understanding data is increasing, uh, the academic world is also trying to bridge the gap between the demand and the supply, and that is why they have started to introduce programs related to data science and different type of analytics, so that the demand that has been created for analysis of data and gathering insights from their data, as that demand is increasing, it has been increasingly being recognized that there's a lot of training that needs to happen from the population level point of view, so that we have professionals who are um, expert in handling problem solving using data science. So that is why in less than 10 years you can see, and this is a evidence of the fact that first of all there is demand of people who can know how to handle, manage and analyze data, and these courses just this plot just shows that aspect. This is another plot, which again talks about what we have already discussed. So the cumulative number of analytics and data science masters degrees awarded in United States, and it's just United States. I could not find data for India or globally, so I'm taking reference of United States. So as you can see that again there is it's almost like a monotonic increase in the number of degrees awarded in data science. So that means that even professionals such as you are also waking up to the field of data science and its importance. However, in this sort of race to become data analysts and number crunchers, what we have lost is perspective, and that is what this discussion will be about. And I will be picking up on specific aspects of data science, and we will try to learn about certain core aspects of data science using these examples. So we have already seen that there's an increasing trend in the number of degrees awarded in data science and analytics. What do you think is the reason behind these trends? What, according to you, is the reason behind this sudden increase in this headlong rush towards data science? Anybody? What is the reason that everybody is talking about data science these days? What is the reason that you have decided to attend this FDP on data science today? The answers are not different. Job opportunities, okay. Helps in predicting whether the business will have profit or loss, okay. So Sagar mentions, but what is helping in predicting what the business will have profit or loss? What is it? Is it data science or is it data? Interest, okay. Data development of model. So I'm not sure how to address. I can't see the person's name. So what do you mean by model development? If you can elaborate. Mathematical application, yes. But if we ask from the very core, everywhere in the world, everybody is talking about modeling, regression, modeling, machine learning, AI, deep learning. But what is the reason behind these trends? Why suddenly our world has woken up to this massive power? What is the reason behind this? Yes, so Sonali is mentioning huge amount of data is available and everyone wants to use it for their benefit. Exactly. So we are living in a world which is inundated with data, and the data is getting generated at, at a very high speed, and our human ability is not able to match it up when it comes to analysis. And that is why, with the use of computer science and statistical and computational domain, this field of data science is coming up. a huge amount of data, yes, and to extract knowledge, these kinds of fields are taking hold in our world. So all of you have excellently identified the reason. So the reason behind these trends is that there's a demand for data scientists. That is why people are pursuing sort of, higher degrees in data analysis. But why demand has increased? Because we cannot deny the fact that there has been an increase in data-driven decision making. So most of the decisions that are made at commercial level or large-scale industrial level in academia or industry are dependent on data. And that is why, because most of the decision making is driven by data, we need people who not only can analyze but also understand why to use a particular algorithm to analyze that particular data. And that is why we can see the surge which we saw in the last couple of plots, that we are moving towards a data driven decision economy which makes decision based on data. And that is why the demand is high, the supply is come, and that is why there has been a surge in sort of programs which help people learn the theory and practicality of data science. But again, there has been a gross loss of perspective on this, and that is why we will be talking about all these kind of things. So these are just few of the newspaper highlights that talk about that data science is here to stay, and every day I think you can see lots and lots of posts talking about the importance of data science. There are YouTube advertisements in which people show about their short-term data science course, which help you to understand data in perspective. So almost everybody seems to be an aspiring data scientist these days. And that is why there is an importance to understand the perspective in data science. Because sometimes what happens is when we rush headlong towards something, we often tend to lose perspective. And that is why I've made an attempt to talk about perspectives in data science. So hopefully the base of the discussion is clear to all of you. Are there any questions before I continue? Okay, so if there are any questions or counter views or counter opinions or something that I may not know, please feel free to share with all of us. Thank you. But there are some things that we are missing, in this flood of data science, and I will show it. So I will be using a lot of cartoons in my presentation and asking you to interpret it. So let us look at this system. I hope the cartoon is visible. Can you see it properly?
Yes, ma'am.
Okay, great. So when you look at this and you read it, what do you understand from it? What is happening in this cartoon? So there's no data classification. Okay. So what is the reason that there is no data classification? Or what is the reason that the other person is saying just stir the pile until they start looking right? What do you mean? What does that person mean by that? And what is it that you're getting? How is this person's attitude showing up in this cartoon? So here there is some data is not segregated. Okay. So there is some sort of manipulation going on over here. You see, this person is saying that the other person is asking, so this person is asking what if the answers are wrong, which is quite a valid question. See, models can be wrong, machines cannot be 100% right. Even Alan Turing's machine had shown us that limit that some problems machines cannot solve. So, but this other person is saying just stir the pile until they start looking right. That shows a systematic manipulation of data to achieve some kind of objective. Now, when we talk about this kind of approach, we tend to lose something called as science. So, When we talk about data science, we cannot talk about data science without talking about the art of research methods and scientifically trying to understand data. So while everybody is talking about data science, modeling, machine learning, deep learning, what we are acutely missing is our strong grasp, our strong fundamental grasp on understanding the research methods deployed in understanding data science, machine learning, or any other field. And that is why as budding scientists in the domain of data science, we cannot isolate data science with appropriate research methods used in data science. So this cartoon exactly showed that if you move in a haphazard manner, you end up manipulating the data in a not so scientific manner, and the insights that are generated are very questionable and indefensible. uh, Satyan Datta mentions data pre-processing. Yes, so data pre-processing is also a part of research methods, but without a proper logic, without a proper reasoning, data pre-processing stands to be questioned. And Thangamani C mentions there's lack of algorithm. Again, the lack of algorithm points to a root cause. So why there is a lack of algorithm over here? Because the thinking has not been very clear. Why the thinking has not been very clear? Because the question that has been formulated is not very precise and crisp. So what I want you to take back from this slide is that data science and research methodology and research methods cannot be isolated from each other. And in fact, when we deal with data, we are talking about data cleaning, we are talking about data pre-processing, we are talking about creating variables out of existing variables. So, and these are all the building blocks of the final insight that we will gather after our model works. So that is why the steps we take towards the development of the final model need to be reasonable and scientifically defensible. If our building blocks are not right, what we arrive will be the wrong answers, and then we will again keep on stirring the pile until we get the right answer without even understanding why we are getting wrong answers at the first place. So getting unexpected answers is opens a whole lot of different doors to understanding data science in a much better way. So I will be proceeding with common errors in data science through certain examples. One of the common errors in data science I've seen is blindness. So this craziness to identify insight. You know, do you agree with me? Before, I mean, I cannot assume that all of you and should not also, but do you really feel that one of the common errors in data science are craziness to identify some kind of insight? What are your thoughts on that? So, when we talk about data science, especially when it's a new field, it's very exciting that, okay, and now I have a pile of data, I will do something and gain some insights out of it, and then publish one or two papers over here. So this craziness to identify insight without forming a solid scientific background is tantamount to, entering into a black hole, and you never really arrive. So that is one of the, and these are all my observations. uh, you know Obviously some of you will find them agreeable, some of you will not find them agreeable, and that's how it should be also. So what I have found is that this craziness to identify insight almost always distances us from following a scientific approach to problem solving using proper methods in data science. So that is one of the common errors. And why this happens is when we approach a data without having properly planned questions. So see, there is something called in computer science garbage in, garbage out. If you give garbage to your system, it will output garbage only. So you have to be very careful about the kind of questions you are asking with your data. If the questions are not well formulated, the approach, it will be visible in the approach, and the conclusions that you will arrive will be highly questionable and indefensible. So this is one of the common things that I have seen in data science, which is this craziness to identify insight at the cost of following scientific methods. So most of the times we often talk about intuition and gut. So without having proper objective analysis, intuition and gut also need some evidence sometimes, especially when we are talking about gaining evidence and information from data. So what should we do? All of us have been fed this idea, okay, data science is the next science of our current world. Uh, if you need to be a researcher, you need to be a data scientist, you need to understand how to analyze data, how to create a model. But so we are being bombarded with these ideas all the time. And that is why we have been an autopilot and become, that kind of road runner, which is crazy to identify insight, but sometimes it helps to slow down and pause and understand the data. Okay, so when you are trying to solve a particular problem, understand your data, sit with your data. Your data is going to give you insights, help you solve problems. Now what do I mean by understanding and sitting with your data? So suppose you have acquired a data set which has around 200 variables, okay, and you may be needing only 10 or 20 of them, but still at least you try to understand the code book of the data and try to understand the variables, the definition of variables, the labels, and the information those variables are trying to provide you. What happens is that when you understand the basic building blocks of your model or whatever you are trying to create, you can do justice to whatever you are doing in a better manner. And it really helps to slow down when it comes to analyzing data and avoiding that road runner approach. Okay, if this model is not working, let me apply this model. No, there has to be a reason behind every methodological step that you take in trying to approach a problem in data science. So get to know your data, explore your data. Now, by exploring your data, I don't mean for reverse hypothesizing, but to understand its variables, the characteristics of the variables, how those particular variables have been denoted in this particular code book. So get an idea of what kind of questions the data set can answer. Okay, and after gaining sufficient familiarity with your data and variables, then formulate proper hypotheses and questions. Most of the time what happens is that there are very basic things. There are two kinds of data, quantitative and qualitative. In qualitative, again, they can be either textual or categorical. Quantitative data can be either continuous or discrete. Now, without understanding the nature of variables, the nature of data variables that you are using in your projects, it becomes very difficult to debug the problem that arise when you're trying to model. Archana is mentioning that, can you please share the attendance link? Okay, I request the organizers to share the attendance link. Thank you. So in order to, not become the road runners and lose the perspective in understanding the insights, you actually spend some time understanding your data, because the time you invest in understanding your data in the beginning will have big payoffs going forward in the journey. Because when the unexpected answers arise, you will not be sad, but you will be prepared enough to reason why that is happening. And once you know why that is happening, then you will be far more objective to take the next steps. Okay, this is not happening as I expected. Now, what is the reason behind it? I will give you a very simple example. Very recently, I was doing a research on, trying to predict diabetic people who are also depressive. So diabetes plus depression and diabetes plus no depression. So what I found out in that research was, as age increases, diabetic people are actually less likely to be depressive. Now this was very counterintuitive to what I thought. I thought, okay, diabetic people, as they age, they should be more depressive because their diabetes may be becoming worse, and old age has its own set of problems. So there should be a case that they should be becoming more depressive. But in my data, actually, I was seeing that there is a negative. The parameter has a minus sign in front of it. So that really led me to think, and then after reading some more research papers, I realized that people who are already diabetic and depressive, over the period of time, they learn how to manage and how to cope their both diabetes and depression. So that was one suggestive hypothesis that I thought could explain the counterintuitive result that I had seen. And so again, uh, variables in data do not always show us a complete picture. When we are dealing with data and trying to model, we often need to refer to literature a lot of times to understand why we are getting something which is counterintuitive or which other authors have not found. So instead of panicking when we obtain answers which are, at the face not very convincing, it is always a good practice to slow down and really sit with your results and then go back, trace back the reason behind it. And this tracing back is extremely difficult when we are a road runner with a craziness to identify the insight. I think this headlong rush to identify insights from the data, either by hook or crook, does not really pay the scientific community, does not pay the time that you're spending, and does not even serve yourself. So one of the first errors to avoid when it comes to data science is uh, not being blind and not being so blind that we are just crazy to identify the insights. Keep your data in perspective, spend time with your data, and try to understand the questions you can get from it. I'll give you an example for this. So since my area of interest is health data analysis, um, examples will be from this field. If you don't understand, please interrupt me. I will try to make it easier for you to understand. So suppose you see these variables in the data. So suppose I have a data set and these are the certain variables I have in the data set. BMI, exercise, so whether you exercise or not, diet, disease, mental health, income, education, and ethnicity. Okay. So when you have this kind of data set, okay, and you have studied the variables. So these are the variables. Now the next step would be you analyze each of these variables. You formulate the hypothesis and analyze the hypothesis given the data set. Do not try to formulate a hypothesis before getting aware of the data that is there. Sometimes what happens is, okay, we have a question in our mind. Okay, so for example, I want to explore how spirituality helps cancer patients. Okay, but I don't have a data for that. So the question is valid, but since I don't have a cross-sectional data to test or validate or my hypothesis, then I have to formulate another approach. The other thing is, okay, I see a data, I explore it, I understand its variables. Based on my theoretical knowledge, I want to explore, okay, hey, this is the question that is worth exploring in this data set. So before you come to that question, you have to be very well aware of the variables that you have in your data set. So that will provide you some perspective on understanding things. So when we are dealing with data, you should really keep your mind open. There are no right and wrong answers, because a hypothesis which is true in a particular data set may not be true for the other data set. So the conclusions are almost always based on a limited space of the data set. Another common error in data science is p-values. How many of you have heard of p-values? How many of you have heard of p-values? Can I see by a show of raise of hands? Okay. Okay. I think. Okay. So so I can see some of you who are showing yes. What about others? Have you ever, do you vaguely remember reading something about p-values? So this is my question. The p-value. So tell me if this is true or false. The p-value is the probability that null hypothesis is true. So those who think this is true, please type T. And those who think this is false, please type F in the chat box. So this was supposed to be a poll, but I'm not able to conduct a poll over here because of admin problem. So how many of you think that the p-value is the probability that null hypothesis is true? Okay. So can I request Sandeep to tell us about p-values? Sandeep, would you like to please share your understanding of p-values with all of us? Or Sagar, would you like to share what is your understanding of p-value? I would like to understand. So those of you who have not read about p-values are very, very common parameters in hypothesis testing when it comes to data science, and highly, highly misunderstood terms in the universe of data science. So this is one of the second common errors in data science, which is p-values. So I will try to demystify p-values for all of you.
The
Yes,
probability
please,
value.
Dr. Vasanthi.
It's something like the probability value.
Probability of what?
Probability of the positive cases as well as the negative cases what we get towards the data analysis.
Okay. Okay. So yes, you're right. It is a sort of probability. And so in my previous slide, this was the question, the p-value is the probability. Thank you, Dr. Santosh. The poll asked the p-value is the probability that null hypothesis is true. Okay, so but this is a false statement. So this is a general understanding of what the p-values people think they are. People think that the p-value is the probability that the null hypothesis is true. No, p-value is not that. I get another response, p-value, if p is less than 0.05, which tells there is a significant difference between the variables, which tells the null rejected and alternate hypothesis accepted. Yes, and there is a lot of scope for understanding p-values right in that statement, because when you say there's a significant difference between the variables, I think this statement can be much more clear and precise. Okay, which tells the null is rejected and alternative hypothesis is accepted. Okay, so I will try to give you a better perspective on p-values on this. Thank you, ma'am, for sharing your perspective on p-values. That was useful. So definitely when p is less than 0.05, the null hypothesis is rejected. So, so this is a definition that I found out from a book in medical statistics, which says that given the null hypothesis is true, the probability of observing what we observed from the data we just analyzed. So when we are doing a hypothesis testing, we generally assume null hypothesis as the status quo, that okay, null hypothesis is true, unless we prove it otherwise using our data science and p-values. Okay, so when the p-value is less than 0.05, that means that the probability of observing such data, so it's the probability of observing the data from which you are trying to gather insights. So if p is less than 0.05, that means the probability of observing such data given the null hypothesis is true is quite less. And even then we have observed that, so that is why the null hypothesis is rejected. The important thing to always remember is that all the insights that you gather from particular data, always remember this is for a given data set. A good scientific researcher will always acknowledge that whatever insights I have observed is for this particular given data set. So let us take an example. Okay, so suppose I am trying to understand the relationship between poor mental health and depression. So to depict poor mental health, I have used a binary variable, which is depression. So 1 means the person is depressive, 0 means the person is not depressive, and gender. So I want to understand whether one gender is more likely to be depressive than the other. Okay, so if depression is 0 and 1 and gender is male and female, what are the kind of variables? What is the nature of these variables over here? What kind of variable is depression? Is it quantitative, categorical, continuous, discrete?
So
Gender
from
is
the categorical data.
yes. Gender is categorical and discrete. Yes. So both of these are categorical data, right? Depression is continuous. Okay. So why do you think depression is continuous? So it can be continuous. In our particular example, I have used 1 and 0. So in that case, it will be binary or discrete categorical. It can obviously be
How it can be continuous now, if you don't mind. How we can take the depression in the continuous value?
yeah.
It may
So
be varying from person to
so you
person
must
and depends on perspective difference.
so there is something called as PHQ-9. So it's a form. So it's I've put it in chat box. So PHQ-9 is a form that creates a score of depression. So it's a score, so when we talk of depression as a score, it becomes a continuous data. I think the score ranges from 0 to 7 if I'm not wrong. So in that case, depression will be continuous on a numerical point. But in this particular example, I have assumed that, 1 and 0 form. So the null hypothesis is, which is the status quo. So, okay, we start off by saying that there is no relationship or association between depression and gender. So the alternative hypothesis would be that there is indeed a relationship between depression and gender, and given a particular data set. So if I take CDC data set, which is Center for Disease Control and Prevention, then I am trying to test this hypothesis. So this hypothesis is coming from my intuition. So okay, there has to be some relationship between gender and depression, but I want to really validate whether or not this hypothesis is right or wrong for a particular data set. So I've used a data set and then I'm checking it by logistic regression and chi-square test. So I've used two tests over here. Most of you may have heard of logistic regression. Chi-square test is used for hypothesis testing between two categorical variables. So whenever we are trying to understand relationship between two categorical variables, we use chi-square test. So when I use these two tests, this is the result I get. So this is the result of logistic regression. Okay. So I think this sex variable 2 means female. The base case is male. And the p-value is highly less than 0.001. Similarly, in chi-square test also, I obtain a p-value which is very less than 0.05. So what does this mean? So my null hypothesis was there is no relationship between depression and gender. When I actually test this hypothesis, these are the p-values I get. So how do I interpret it? Now, what do you think of the null hypothesis given the response from logistic regression and chi-square test and the p-values? How do you interpret it? Okay, yeah, so there is a significant difference between male and female with respect to depression. Yes, so that means that the null hypothesis is what? Is it rejected or it's not rejected? It's rejected, absolutely. So now that we have seen that we started off by saying that, okay, our null hypothesis is true, but when we analyze it, we saw that, the probability of getting a data which tells that there is no relationship between depression and gender is very less, and still we have observed it. So that means that there is some problem with the null hypothesis. We cannot we have to reject it. So in our data set we actually find that there is a relationship between depression and gender. So what does this mean? We started off with null hypothesis saying there is no relationship between depression and gender. Assuming the null hypothesis is true, the probability of obtaining data as extreme as we got is less than 0.0001. This means it is highly unlikely to see something like this till we observe it. So therefore, our starting point, the null hypothesis, is to be rejected. So there is in fact a relationship between depression and gender. In fact, the odds of depression among women is 1.68 times the odds of men. So if you're wondering where this value has come up, so from logistic regression, this is the coefficient for female I got with the base 2 male. So when I raise 0.52, when I convert it into the odds, so it will be e raised to power 0.52. So the odds of depression among women is 1.68 times the odds of depression in men. So that means I started off with there is no relationship between depression and gender, but here I can see that women are more likely to be complaining of depression as compared to men. So this is how p-value actually help us to understand. And if I were a better researcher, I would have added the odds of depression among men is 1.68 times the odds in men in a given data set. So I have not added that over here. So there is scope of improvement. So this is how p-values help us to understand things. So, generally in the domain of data science, especially in social sciences and humanities and public health, p-values are the make or break factor for the research and conclusion, and they are dealt with very frivolously. So, but p-value is not the end of the story. It's not everything. There are situations when p-values exceed 0.05, but still it is difficult to justify. So let us learn to look beyond p-values and try to really understand what is happening. But always remember, whatever the p-values we are obtaining it in a given data set. So there are certain serious problems with p-values. Why? It only tells us about the hypothesis as observed in the given data set. The finding may or may not be universal truth. We might find if we take data from some other cultures, let's say Japan, and then we try to understand the relationship between depression and gender, we might say, okay, there is no difference at all. Males and females are equally likely to be depressive. So in that data, we might not find what we found in this CDC given data set. So always exercise good amount of scientific objectivity and skepticism when looking at p-values. They do not reflect universal truth, and they always talk about the given data set. And we do not get to know about the cause and effect relationship using p-values. For that, we obviously need experimental studies. So a p-value greater than 0.05, where you expect p-value less than, can open your eyes to something beyond just p-values. Sometimes what happens is we get so fixated on getting p-values less than 0.05 that we ignore everything else. And when we ignore everything else, what we ignore is perspective. What we ignore is, the reason behind why we are observing what we are observing. And sometimes when we don't get p-value less than 0.05, we are very disappointed, sitting in despair and thinking, okay, my research is doomed. I'm not getting significant results. No. From my experience, what I've noticed is not getting expected results can open a whole lot wider door of exploring the problem in a much more richer, in a better manner. So let us try to learn to look and go beyond p-values. Sometimes when we don't get expected results, we have to dig deeper. Is it about the data? Am I messing up with my methodology? Have I not understood my variable properly? Am I using categorical as a continuous variable? Am I using, have I miscreated the categories in the variables? Is there any confounding variable? There are so many reasons that can explain a p-value greater than 0.05. So instead of getting disappointed about it, try to really understand why is it happening. And when you have done your homework and even then it is greater than 0.05, then it's good time to discuss it with others, show your perspective and try to gain perspective from someone. But please do not fixate on reducing your research to obtain a p-value of less than 0.05. Another error in common error in data science is lack of objectivity. And this is highly common because we are living in data-driven economy, and somehow we consider the person as smart who can just do some number crunching, give us some results. But the sad thing is they must also be able to explain the reason behind why the data is behaving the manner it is behaving. So lack of objectivity is one of the common things I have noticed in data science. Again, it is linked to blindness. When we are blind, when we are crazy to identify insights, we end up becoming less objective, and that is why our research falters. And then when we send our paper to some journal or conference and it's not accepted, and the sad thing is that the peer reviewers have also not given us any comments, then we're really scratching our head and trying to understand where have I messed up. But the reason lies really in the fundamental building blocks of data science, and it is always linked to research methodology. So instead of when you get a response from your data which is not expected, do not disappear. And most importantly, do not adjust your data to conform to your preconceived notions. That is highly unscientific. So what happens is, somehow I also see that there's a lot of image also attached to being a good data scientist and good number cruncher. And when our system is not working as expected, we tend to take it personally. But there has to be a gap between the result of your work and your brain and your mind. You have to be able to look at a situation in an objective manner. And not getting what is expected is always, a good sign of the fact that there is learning that needs to happen beyond it. Okay, so lack of objectivity is one thing. So that often leads to data dredging. Any one of you who has heard of data dredging? You can raise your hands. So data dredging is sometimes referred to as data fishing. Is a data mining practice in which large volumes of data are analyzed seeking any possible relationship. So you have a given data set and you are testing all the possible hypotheses on your data set. So, okay, so suppose you started off with hypothesis H1, you found, okay, I cannot reject it. So you just throw it off without even understanding why it is happening. Then you formulate another hypothesis H2, you see it, and then you keep on doing it unless you find some hypothesis which is actually being rejected based on a data set, and then you stop over there and then you say, hooray, now I found a p-value less than 0.05. But this is a highly unscientific practice because there is no basis to which, first of all, you have rejected the hypothesis that you have rejected, which were not being found properly in your data, and then ultimately narrowing down to the hypothesis. So this is like a trial and error. Just to prove a point, just to gather some crazy insight, you are doing trial and error with your data, and this sort of practice is called data dredging. That is one way to look at data dredging. The second way to look at data dredging is trying to manipulate the data until and unless you get what is your preconceived notion. Okay, so that is again highly unscientific and unfortunately quite prevalent at university levels, especially. So the process of data dredging involves testing multiple hypotheses using single data set by exclusively searching, perhaps for combination of variables that might show a correlation, and perhaps for a group of cases of observation that show differences in their meaning. So you see, you are basically dealing with your data in a very unreasonable, unscientific and unguided manner. And you have a data set and you are just throwing your darts everywhere, and you just looking for a position wherein it fits perfectly. So again, this literally makes a mockery of data science. It's quite a common practice in data science, and especially done when we lose perspective on gaining, when we lose perspective when we receive a result which is unexpected. So try to read more about it. In the limited time period span, I cannot discuss much on it, but data dredging itself deserves a individual session because it's quite a rampant practice, sadly. Okay, moving on. Okay, another common error in data science: correlation is not causation. I am sure all of you have heard of this. So if you look at this cartoon, how will you interpret this plot? What is going on in this cartoon? Anybody? Any hints? So as you can see that there is a sales, there is an increasing trend, and shaved heads is an increasing trend. And one of the person in the team is mentioning, we found this correlation in the data, everyone take a result. So they're falsely believing that as the number of shaved head increases, the sales of their product will increase. So one of the common errors in data science is correlation is not causation. A salesperson should be groomed well. Okay, in what terms? You might like to explain. So the thing is that just because two variables are correlated doesn't mean that there is an explanation behind what we are trying to see from that. Just because shaved heads and sales are interlinked uh, doesn't really give us enough fodder to make any decision, especially in a business enterprise. So whenever you find, first of all, people get very excited when they find two variables correlated, V1, V2, and they are highly correlated, and then they jump over their seats and think, okay, I have found correlation between these two variables. Now my life is sorted. I can say and can speak on and on about how one variable impacts others. No, when two variables are correlated, there has to be an accompanying theoretical story that justifies why these two variables are correlated and what is the implication of this correlation. The implication almost always is not causation. It can be many other things as well. So be very careful when you notice two variables as correlated, rather than at the face value trying to justify why this correlation is important. Sit with your team, sit with yourself, and try to understand, okay, does this correlation even make sense, and take it from there. So causation is more related to longitudinal studies. So generally when we want to establish cause and effect, we do experimental studies. For example, in 1950s, when cigarette smoking was shown to be a causal factor for lung cancer, an experimental study could not be done, obviously, because you cannot ask people to smoke and then observe them for a period of 20 years and see whether or not they develop lung cancer or not. But it was a highly systematic study, and that was able to prove that, okay, smoking does cause lung cancer over a period of time. But correlation does not always imply causation. If there is a correlation, it may or may not be causation, but to establish causation, you need experimental studies. When we want to do causation, we start off with people who do not have that disease. Suppose if you want to understand a particular variable causes disease, so you ideally would start with people who do not have disease, observe them over a period of time. Half of them would be having the risk factors, half of them will not be having the risk factors, and after a period of time, you see whether or not they develop the disease or not. So that way you can establish causation, but correlation does not mean causation. A and B may be correlated without there being any causal relationship. So for example, let's say example of depression and gender only. Gender and being depressive is correlated, but doesn't mean that being a woman causes one to be depressive, right? So when you establish causation and correlation, there has to be an accompanying theoretical base to justify that. Without that, do not simply take correlation at its face value. Try to dig deeper and understand what could be the accompanying story. So for example, ice cream eating is correlated to having sunburn. Okay, so for a moment, forget there is a sun over here. So ice cream, so you are a researcher, you are trying to do a research in summer, and you see that ice cream eating is related to sunburn. Now, if you didn't know that, even if we didn't know that correlation is not causation, we would be guilty of assuming that eating ice cream leads to sunburn. Okay, if we follow that correlation is causation, then we will feel that, okay, ice cream eating leads to sunburn, or having if someone has sunburn, they eat ice cream. But what is the confounding variable here? It's the dry, hot, and sunny summer weather. Because in summers people eat ice cream, in summers people tend to go to beach and they get sunburn. So it is the sunny weather which is actually the variable that can explain both the ice cream eating and sunburn. But if you just look ice cream eating and sunburn and you see that they are correlated, then we all might be guilty of linking ice cream eating and sunburn, where there is no relationship at all. They are actually related to a third variable, which is a confounding variable, which is very, very hot summer weather. So the takeaway point is, whenever you find two variables correlated in your respective research, that doesn't have to be the ending point, that has to be a starting point, because that encourages you to explore, okay, why these two variables are correlated. What is the theoretical explanation for this? Am I able to arrive at a theoretical explanation for this? If you are, Then you look at the evidence for that from some other papers. If you are not, then you try to discuss it with your team members or researchers or instructors, and then see. But at the face value, there is a lot more going on beyond correlation. So do not make this error of assuming correlation as causation. Okay, moving on. Fourth error I want to talk about, which will provide you a perspective in data science, is a poor logic for cleaning data set or removing outliers. So most of the times, when we are doing data analysis, we are involved in data cleaning and data pre-processing, and almost always we remove outliers. But how do you decide which data points to remove? How do you decide that this particular point is an outlier? This particular point is not an outlier. On what basis do you define these variables, the specific values of variables, as an outlier or not? Again, data cleaning, data pre-processing are vital steps, and there has to be a clear and precise reason as to each step you take. So this is also one of the common errors in data science, that your logic for removing or cleaning the data set or removing outliers has to be defensible and reasonable. So many times researchers mindlessly cut short their data, but every decision in the process of data analysis must have an accompanying logic. Otherwise, it is dubious. When the peer reviewer is reviewing your manuscript, and you mention that, okay, I removed this data point, full stop, but you do not mention the reason, therein only there will be a huge void that reviewer will question. Okay, this person doesn't know why he or she is doing this kind of thing, and there is serious question on their methodology. So they will not even bother to look at the results, because when methodology itself has some flaws, then obviously the result will be difficult to approve of. So while cleaning variables in the data, a reason as to why specific values need to be removed. They're blank, they're missing, they're not really telling anything. If you think they're not really telling anything, why do you think so? So you have to ponder over these decisions and discuss when confused. So it helps to really slow down when you're doing data science and methodology, because slowing down and actually sitting with your data can really help you develop a better perspective and save some poor decisions going forward. So I will give you an example. So there are two variables, x and y, and these are hypothetical variables. Okay, so I have just plotted a regression line over here. So this was my data set, and these are 2 points. So when I plot a regression line with outliers, this is the line I obtain. But when I remove the outliers, this is the line I obtain. So according to me, these two are the outliers. But if you want to remove this, there must be a solid reason. Otherwise, the regression without outliers will be very questionable. So if you cannot tell me, or if I cannot tell you why I am removing these outliers and just draw this line, so this without outlier regression line is highly questionable. And most of the time, sadly, people think that outliers means points that are not lying on the line. No. Outliers can sometimes also mean they are trying to give you some other information that other points are not giving. So you should not only be careful of the decisions you take before removing the outliers, but after modeling your data, you should also see the impact of the outliers, both absence and presence. Okay, so even outlier removal has to be a very thought of activity. Otherwise, if you show this, okay, this looks like a very beautiful line, all the points are fitting, in fact overfitting, but you cannot justify why you have removed these two outliers, nobody will even bother to look at this without outlier, because your scientific objectivity is highly questioned over here. So in data science, it is personally useful and professionally admirable to show the reasons behind each step that you take in data science methodology. So, but sometimes what might happen is, okay, you have this data x and y and all the points are aligned over here, and then you have this point, which is although falling in line, but it is away from all the points. So if you saw something like this, then would far end point be an outlier? So what does the audience think? So if I show you this kind of data, What do you think of the highlighted point? Is it an outlier or is it not an outlier? Yes, Pallavi? So those of you who are saying it's not an outlier, can you also justify? Can you give a reason also why you think it's not an outlier? It's on the regression line, okay? Okay. So what if it was not on the regression line? What if it was somewhere here where my cursor is? What if it was here? Then would you call it an outlier? It's near to mean. So is being on the regression line an indicator of whether a point is an outlier or not? Pallavi, I see your hand raised. Do you want to say something? So based on the explanation that I'm seeing, is it a general understanding that if a point is on the regression line, it is not an outlier? So suppose if the point was here, would it still be not an outlier?
My idea is, madam, we used to frame the cluster.
So,
We used to frame the cluster based on the points.
okay.
If the value which is not within the cluster value, which is outlier the things, something like that, I can say it is not satisfying the cluster depending values, then we are going to call that point as an outlier.
Okay, okay. So as for what you said, if a particular variable, so if all the variables in the x are supposed to be less than 10, and if I see a variable x which is 20 and it is sort of deviating from the existing point, then I say it's an outlier.
Yeah,
Yeah.
yeah. It
Okay.
point is different from the relationship that is existing among the depth points.
Okay. So let me try to give you another perspective on this. Okay. So let us see this. What if I told you X is the weight of animal and Y is the weight of animal's offspring? So let us see. So I'm showing animals and their offspring. And suppose if X is the weight of the animal and Y is the weight of the animal's offspring. So in that particular situation, what happens is that most of the animals will lie here, but there will be some animal which actually lies over here. So in that case, it's not really an outlier. It is telling something more about the data set. It is maybe telling us something special about the data set, which all the other points are not telling. Okay, so that is why before you label some point as outlier, make sure that it is, maybe it is some different or unique case which is telling us something which is very different. So maybe if this plot is about the weight of the animal and the weight of the, so if x variable is the weight of the animal and y variable is the weight of the animal's offspring, then most of the animals lie here. And if I see this point, maybe this is related to elephant or dinosaur, if dinosaurs are still living. Okay, so in that particular case, it's not really an outlier, it's just telling us something more about the data set. So is that point clear to all of you? So before you remove outlier from your data, have a very solid reasoning of why you think it's an outlier and why it needs to remove. Create two models, one with outliers, one without outliers, and then see how your model gets impacted in validation and testing phases after you remove outlier. So there's a lot of dirty work that needs to be done when in the process of creating a model, and most of the people sort of bypass it, but it comes back to bite later. Okay. Another common error in data science is fitting the model without a prior concept. As I've already said, it's called data science, it's not data magic. So when you take hold of some data, make sure that you understand it, you understand the variables, and then you plot the questions, formulate the question that your data can answer. Do not become blind to identify the insight crazily. So most of the time it happens in predictive modeling, especially with the advent of data science, deep learning. We have short-circuited our understanding of different variables and how different features are fed into the model, because the feature extraction happens automatically, but that should not stop us from trying to gain a deeper perspective on the variables that are being used to model a particular output variable. So when you have a data set, you should have a clear understanding of what is the question that you want the data to answer, and is it really able to answer the question that you want to ask. So this is the old paradigm. You know your mission, you identify the data sources, you clean and organize your data, you perform some statistic analysis, you draw conclusion. But I propose a newer paradigm in which you don't really know your mission. I mean, it's not really always possible to know exactly what you want, the information that you want to obtain from your data, but you have a slight hint of what you want to do, what you want to obtain. So you identify suitable data sets. When you identify suitable data sets, you want to explore which data set is appropriate. So to decide which data set is appropriate for your research question, you identify the variables in the data set. And once you identify the variables in the data set and then you choose a particular data set, then you refine your question. Now you have a hint. So you have a hint with which you started. You had a set of data sets, you explored the variables. Now you know the variables, you have a hint, and based on the collaboration of that, you try to refine your research question and you try to make tighter and tighter and tighter. Only a tight research question reveals, good results and conclusions that are defensible. Even after you have refined your question, you again explore the variables in the data set, and these back loops also show that you go back again to from where you started. So this is like a feedback thing that is happening all the time, whereas in the old paradigm there is no scope of going back. So so be thoroughly engaged with your data set. Don't just look at it as a means to give me some insights, some p-values. No, thoroughly engage yourself with it, and try to see what it is trying to tell you, what you can get out of it. Not in a very utilitarian manner, but in a very artful manner. Like, okay, I want to really understand, is there anything that this data can tell me? So then explore the variables in the data set and then perform statistical analysis and modeling. So at each step, pause and reflect, pause and reflect, pause and reflect, rather than doing things in a very linear, straightforward manner. And the more you discuss, the better perspective you obtain, the clearer and cleaner your research work is. So that was about the common mistakes in data science. A few of the suggestions for data science pedagogy for self and students. Project-based learning is the best way to understand the different nitty-gritty of data science, modeling, AI, machine learning, deep learning, whatever you may call it. Always work on raw data sets. Already pre-processed data sets, pre-clean data sets don't teach us anything. If you want to really learn the concepts of data science, you have to make a point to start working on the raw data sets, which are dirty, noisy, or full of variables, blank values, missing values, and then try to build on your understanding from raw data sets. Try to take data sets from already established organizations, for example, WHO, World Bank, CDC, OECD, national surveys, and do not default to Kaggle dataset. Kaggle dataset, most of the students have seen use Kaggle datasets, but Kaggle datasets are already very clean, very neat and clean, and the only thing that you can do in Kaggle datasets is apply a model and see its accuracy, which also serves a purpose. I'm not totally denying the utility of Kaggle dataset, but if you really want to, understand the end-to-end process of data science and data analysis, I absolutely encourage you to start working on raw data sets. When we work on raw data sets, raw data sets, as I've already mentioned, are dirty. So they are not very clean. So there is more scope of learning about data processing, cleaning, and diversity of variables that can be used to tackle a problem. So you are exposed to the real ground of data science, and then you can actually learn step by step the aspects of data science. So I will demonstrate this with a very simple example. For example, you wish to study the gestational diabetes risk factors. Okay, so GDM, as you know, is diabetes in a pregnant woman. When she is pregnant, often women develop high glucose, and that is GDM. It is a risk factor for both mother and child. So, as a scientist, you want to understand what are the risk factors that a pregnant woman develops diabetes during pregnancy only. So, GDM is diabetes during pregnancy only. So, you want to study the gestational diabetes risk factors. And the given data set that you are used for this study has following variables. Do you have diabetes and are you pregnant? Okay. So from this data set, you want to identify that who are my cases, who are GDM positive and who are GDM negative. So if in your data book, you have this variable, do you have diabetes? And there are 4 values, yes, no, yes, reported in previous pregnancy and pre-diabetic. How will you reason, how will you create a GDM positive and GDM negative case from this? Any guesses? And so this is an example of working on the raw data sets wherein you do not have a clear demarcation of GDM positive, GDM negative, but you have some hint about the diabetes status of the person, and based on that you need to identify the GDM positive and GDM negative. Yes, Pallavi? I think you are muted. We are not able to hear you. So this is one of the examples of working on the raw data sets, because raw data sets do not provide us, they do not serve information on platter, whereas Kaggle data set serves information on platter. Kaggle data set is mostly serving the Kaggle people, not the scientific community or academics like you. So if you really want to ace your game in understanding data science, you have to start working on raw data sets. So if you had these options, then you can say that, okay, I cannot clearly identify GDM positive, but I can assume that people who have diabetes and who reported it in previous pregnancy and who are pre-diabetic are more likely to be GDM positive. So the cases like 1, 3, and 4 can be reasonably considered to be GDM positive, whereas the case with no is GDM negative. So this is how you create GDM variable from the existing variable, also giving the reason that why you have included the cases 1, 3, and 4 as GDM positive. So this is the advantage of working on data in raw data sets, because they give your mind a very good exercise about data science. So lastly, a few of the best practices in data science. A literature review is very important. You must see how others have solved the problem that you are tackling. This helps us to gain deeper perspective on how others have tried to solve the problem that you are solving. Do not get disappointed when you see that your method has already been proposed. Every research has its limitation. Just because someone has already done it should not stop you from pursuing it. They have not done it your way. So continue to focus on your problem, but try to see the limitations in the existing work also. Critically review their work before formulating your own research question. As much as critical review and literature review is important in research in general, it is very important for data science. Data science fundamentals are non-negotiable. As I mentioned, that in the craziness to identify the insights, the fundamentals have taken a back seat. But the person who emerges winner in the final term is the one who will have strong hold on the fundamentals of data science: p-values, statistics, computations, probability, distribution functions, and all these kind of things. Keep working on raw data sets. I think raw data sets, if you start a practice to work on raw data sets, you yourself will feel that your critical thinking ability, problem solving ability, conceptual formulating ability will increase drastically if you work on raw data sets and use them to analyze and seek review on your work. Try not to force insights. Try to work in collaboration with your data rather than reducing it, to your slave. So try to collaborate with your data. And who is a perfect data scientist? It's just a cartoon I obtained. Sort of captures pretty fine. A good data scientist should have an open mind, creative, analytical should have a human interest, and it's okay if they do not know how to do business for now, but an open mind is very important thing, and analytical and human interest according to me. So this was about data in numbers, and there are some places to polish data science concepts. I will share this PPT with the organizers who can share it with you. Stanford University provides amazing MOOCs on data science, and they are free. So please use them for polishing your data science concept. The way they explain the concepts is really great, and I have personally used them and found them very, very useful. Towards Data Science is another website. KD Nuggets is another very useful website if you want to polish your data science concepts. You can follow lecture notes of other national and international universities. Read books on data science, make mistakes faster. And the only way to make mistakes faster is to work on raw data sets. So even if you don't do all these kind of things, but you work on raw data sets, I'm sure that all these websites, whatever they're talking about, you will automatically learn when you are working on raw data sets, which are noisy and dirty. So that was about structured data, which is numerical data. I have added only 2 more PPTs for unstructured data because I thought that it would be nice to provide you a brief perspective on this. So what is the single truth about machine learning? What do you guys think? What is the single truth about machine learning? So it's about numbers, vectors, okay? For any machine learning model to work, we need to feed numbers. But what about if the data is textual? What if your data is not numerical, but it's words, sentences? What do you do? So there comes a field called as NLP, and I'm just going to briefly touch on it, just on 2 slides. So NLP stands for Natural Language Processing, and it is one step beyond data science. So some of the salient points about NLP is that data science is normally about data, but data generally is in form of numbers. But in NLP, what we are trying to do is we try to reduce a sentence into its vector form. Now, how that sentence is reduced into a vector form, that depends on the methods we have used, and how closely a vector resembles the semantic and syntactic meaning of the sentence, that is reflected in the results of the modeling. So few of the common ways of reducing sentence to vector forms are bag of words, term frequency, inverse document frequency, and more popularly, some very commonly used word to vector form. So NLP is basically more sophisticated mathematics. It's also a part of data science in some way. The only difference is that the data in natural language processing is unstructured data. So example of some research problems in NLP is sentiment analysis. So generally Amazon reviews, YouTube reviews, or Twitter sentiment analysis, sentence similarity, when you are trying to chat with an online bot and the bot is trying to understand the sentiments of the person and then formulating a proper response. Recommendation engines, whether be it on Netflix, YouTube, or Flipboard, okay, and question and answer automation. So these are some of the problems in NLP. NLP is also a good field to explore, and again, I would say it is sophisticated mathematics only, because in that you are trying to learn how to reduce sentences into the domain of numbers. Idea is always to start small and be consistent. So that was all from my side. A very small attempt to discuss the perspective on data science. Again, we should always remember with great data comes great responsibility. And I'm always happy to collaborate. You can write to me. I'll share this PPT with the organizers. So thank you so much.